doing some graphing, we're going to use this app over here. This is Desmos.com. Really, really solid app. So, I mean, really good for graphing and stuff like that. It's pretty dynamic too. You know, like you could do something like y equals mx plus b. That's maybe a formula some of us are familiar with. And then it's saying like, well, what's m and b? Did you want to like add a slider to those? I'll say, yeah, sure. And so now it has this graph, and this is y equals 1x plus 1. So slope of 1, y-intercept of 1. And then, you know, we can like switch up the slope if we wanted to, switch up the y-intercept. So that's kind of cool. It's nice and dynamic. It's really responsive. Yeah, Desmos. It's spelled like this with a .com at the end. So Desmos.com/calculator. So we're going to be using that today. I mean, if you want to follow along, you can go ahead and go to Desmos.com/calculator. Really, really, really useful thing. I use this a lot in my teacher days. Anyway, going back to over here with the apple boxes, we have K apple boxes full of apples. Each square box of size M contains M times M apples. You just noticed two interesting properties about the boxes. Number one, the smallest box is size 1. The next one is size 2, all the way up to size K. 2, boxes that have an odd size contain only yellow apples. Boxes that have an even size contain only red apples. Your task is to calculate the difference between the number of red apples and the number of yellow apples. So basically, we want to do red apples minus yellow apples. I think, yeah, red minus yellow. Okay, so they give an example, 5 over here. I'm not going to draw this out because it would take forever, but basically, you know, imagine you've got a box with just 1 yellow apple, and then one with 2 by 2, so I guess 4 red apples, then one with 9 yellow apples, then 16 red apples, then 25 yellow apples. And basically, we want to look at the difference between them. So we're going to do this in 3 ways. And then we're going to make comparisons about those ways. Okay, that's going to be the idea here. Oh, geez, I forgot to talk about the time complexity of the last one, but I guess we'll get into it here. So, okay, basically the idea is we want to count our apples, right? We want to count the apples of each type. So I think the sort of straightforward, more naive interpretation would be to do something like this. So we'll say red apples is going to start as 0. And what is it, yellow apples? It's also going to start at 0. There wasn't a yellow apples emoji, so I used green apples on my Twitter update, but oh well, close enough. Okay, so we're starting with 0 of each type, and then we basically just want to run through our box numbers here. So I'm going to use n to represent that, and n is going to be less than or equal to k. We'll just do n++ because we want to go through every single one of these things. And yeah, Rainbow, I like Desmos too. Isn't this super useful? Let's continue with this. So we'll say if n mod 2, and you know, like we could say if n mod 2 equals 1, or if n mod 2 equals 0, but we could also just say if n mod 2, right? Because if it's 1, it'll typecast to true. If it's 0, it'll typecast to false. So basically, if n mod 2 is 1, what do we want to do? In other words, if this is odd, what do we want to do? Well, we want to do yellow apples plus equals n times n. Right? Because that's going to be the size of the box, the apple box, right? Otherwise, we'll put in the red apples. Plus equals n times n. There we go. And then what do we want at the end? Well, basically, we want to know the difference between the red apples minus the yellow apples. I mean, that's what the doctor ordered, right? Okay, yeah, there we go. So we could just submit this and be done with it. Great. That wasn't too bad. I'm just waiting for this thing to go away. Thank you. Okay, so let's go back over here. I'm going to do a modified version of this. Okay, so I'm going to take this. I'm going to reset the code, confirm that, bring this down here. This is going to be appleBoxes 2. Okay, because 1 is actually going to be something a little bit different. I'm going to keep it the same for now, but then a little later I'm going to modify it. Okay, I'm going to make an important modification. All right. So, what's another way to do this? So, yeah, we should probably talk about this one. All right. We're going to look at this in, yeah, kind of a math way. So we're going to go over here for now, and we're going to take a look at our apple boxes. I guess we have red. Yeah, we have red and yellow. We can use both of those. We don't need to add any new colors. So, actually, wait, hold on. We want the box number, right? So like n. Okay, n is going to be our first thing. And then how many apples, I guess, is going to be the next thing. So I'll just draw something that maybe kind of looks like an apple. Yeah, okay, cool. And then I guess we want sort of like the sum as well. That's another thing we want to be sort of keeping track of. Okay, so for n, we're going to have like, it starts at 1, right? 1, 2, 3, 4, 5. We'll start with 5 for now. If we need more, we can get more. I think it begins with yellow, right? So 1 times 1 is just 1. So 1 yellow apple. The next yellow one is going to be 3. So that'll be 9 and then 25. Just wanted to get all the yellows out of the way so I didn't have to keep switching back and forth between colors. And then this one will be 4 and 16. We might as well, just for the sake of evenness, fairness, we might as well just put in a 6th one there. Yeah, I feel better about that. Okay, so keep in mind, we're subtracting the yellow ones from the red ones, right? We're doing red apples minus yellow apples. So we could sort of think about this in a different way, right? Like okay, actually here, this is a little intermediate step. I don't think this is going to make a huge difference, but we could just say something like this, like let total be assigned the value of 0. And then for here, we could just say total, if it's yellow, total minus equals that. And if it's red, total plus equals that. And then we just return total at the end. I mean, would that work? Yeah, that would work. So that's kind of the way I want to think about it here, just in terms of our total. So in terms of what we're adding to the total, the yellows are negative, the reds are positive. Okay, so we got something like that happening. Great. Now if we actually start adding these up, well, our sum is going to start at -1, and then we add 4 to that, so we're going to have 3. And we add -9 to that, so we'll have -6. And we add 16 to that, so we'll have +10. We add -25, putting us back into the negatives at 15. And then we're going to add 36 to that, which will put us at 21. Folks, these numbers look familiar. I feel like we've seen these before. We've got 1, we've got 3, we've got 6, we've got 10. Hey, it's the triangular numbers. In other words, the sum of all numbers from 1 to n, right? That's basically what we're looking at. Now we have positives and negatives, so we'll deal with those in just a sec. But the main thing is, well, what's the area of this? If you recall, we took a look at a proof of this a while back where we found that it was going to be n times n plus 1 divided by 2. And I think there's a name, there's probably a name for this formula. Where I first heard about it was from Carl Gauss as a schoolboy. His teacher was trying to keep him occupied, I guess, and they were like, add up all the numbers from 1 to 100. And apparently he did it in like seconds because he came up with this method. Anyway, point is, I think Magical Well was one where we sort of looked at that. I know we did something a lot more intense for Magical Well, but that was task 27 of the core, in case you wanted to take a look at that. Okay, so we sort of have an idea of what this is going to be equal to. It's going to be n times n plus 1 divided by 2. But how are we going to handle this negative thing, right? So basically, wait a sec. N times n minus 1 divided by 2, Rainbow? But that's for something different, though, isn't it? Like, wouldn't that give us the previous one or something like that? Again, well, let's test it. So, like, if we were looking at 4, let's say. So, 4 times 4 plus 1, which would be 5. That'd be 20. Divided by 2, we get 10. So, yeah, okay, we want the plus for this one. Okay, so basically, we've got this. And then we want to deal with this negative over here as well. So basically the negative is only appearing for odd values of n. So we could do something like this. We could say like -1. Well, keep in mind, like -1 is an interesting number because when you multiply it by itself, it becomes +1. Multiply by -1 again, and you're back at -1. So it's not changing the value, it's just changing the sign. So because of that, we could do something like this, right? -1 to the power of n. Well, actually, it would have to be more like n minus 1 or n plus 1, I think. because the idea here is that we're going to have, or is it? No, actually, that's my mistake. No, it's just going to be n, because negative 1 to the power of 1 is going to give us negative 1, right? And then negative 1 to the power of 2, that's going to give us positive 1. So there's an imaginary positive 1 multiplying this 3 out here, right? To the power of 3, we'd have a negative. To the power of 4, we'd have a positive. So basically, we're going to have this thing times this thing. That's going to be the idea. And we'll use k for that, I guess, because, you know, that's where we actually want this thing to stop. So we could say just something like this. Return negative 1 to the power of k. And should I parenthesize that? Maybe I should, just for the sake of clarity, if for no other reason. We're going to multiply that by what we had a minute ago. So k times k plus 1 divided by 2. Semicolon. Let's see if that works. Yeah, it does. Okay, cool. So, nice stuff. That's very good. Okay, so let's see. We've got two different ways of doing this. I'm going to call this one appleBoxes 3, and we'll cut all that. We'll reset this, and we'll paste it back in. Okay. Now, I'm not actually going to do, well, okay, technically I'm going to do one more method. It's going to be really silly. So notice how appleBoxes 1 and 2 are the same. I'm going to sort of differentiate them a little bit here. I'm actually going to put like a little function in here, and it's going to be box. Okay, we want to find like the size of the box. So box, and we'll say size, okay, something like that. So what do we want to do with this thing here? Well, basically, I'm not sure how extreme I need to make this, but because we want to sort of illustrate this concept of time complexity, like big O and all that kind of stuff, I want to make this one less efficient than it is. So instead of just squaring the number over here, I'm using this box function. And I don't know, I think I'm just going to make it something kind of silly. So I'll say let apples be assigned the value of 0, and ultimately we're going to be returning apples here. I think I'm just going to do this. So just while apples is less than n times n, apples times equal, that should be size, I guess, right? So while it's less than size times size, apples plus equals size. So I don't know, it's silly, like this isn't something we ever really do, but it's something we're doing here just to kind of slow it down. So we'll say not n times n, we'll say box at n. And same thing with this one, box at n. Okay, so why are we doing this? Well, it's because we want to know how these things are running. We want to know, like, how long does it actually take for these things to execute? So we're going to do some tests over here. Now, one thing I want to say, we're going to have to add up some numbers here. So if any of you guys in the chat want to help out here, get your calculators ready, because I'm going to need to add up a bunch of numbers here, okay? So I appreciate any help you can give me with this. I'm not a big math guy. So, okay, here's what we're going to do. We'll say, let's start time. Be assigned the value of new date. And then we also want to have end time. Also be new date. And what we want to return here is end time minus start time. And yeah, Rainbow, no worries, man. That formula you gave, I think, would actually give us the previous one. So I think that would be the sum of all numbers up to but not including n. I could be wrong about that, but I think so. Because like if we were to put, if we were to do like n times, if it was 4 again, like 4 times 4 minus 1, that'd be 4 times 3, which is 12 divided by 2. We would get 6. So I think that's just the previous one. It is a formula. Like I definitely have seen that one as well. So probably more of a mix-up than a misremembering. All right, so while, what do we want to be doing here? Actually, not even a while. Let's do a for. So I'm actually just going to execute the code a bunch of times. Well, actually, here, let me show you the principle behind what I'm doing here. appleBoxes 1, let's say, at, I don't know, 10. Okay, so we're just going to run appleBoxes 1. We have that function. It's down here. It's showing up green because it's being declared down here, but because of hoisting, we don't need to worry about that. It should still know what appleBoxes 1 is all about. Notice it's giving us 0, 0, 0. You know, perhaps we could have like a really big number in here that would actually take some time. Yeah, 5. So that took 5 milliseconds, 4 milliseconds, 1 millisecond, 0 milliseconds. So these are the kinds of things I want to be like adding up. So in a minute, I'm going to ask for you guys' help on that. But the thing is, notice that like our least efficient algorithm, even with an enormous input, something that's like orders of magnitude higher than the maximum possible value given in this problem, it still only took like 5 milliseconds. So that's not really enough. Because of that, I actually want to repeat this a bunch of times. And also that's going to give us like kind of an average, I would say. So let's start with 1,000, I guess. I++, and let's get a more reasonable number in here. Maybe 40 would be a good one to start with. Okay, so that took 8 milliseconds here, 4 milliseconds, 1 millisecond. Folks, I don't think it's enough. Let's try, what's that, 100,000? Okay, these numbers are looking a little nicer, or, you know, depending on your perspective. They're looking bigger, that's for sure. If I were to do, for example, appleBoxes 3, what's that saying? 5, 5, 3. What about 2? Actually, let me shrink the input a little bit. I think this is going to work. But let's multiply this by 4. So about 400,000. I think that's going to be a good number. Or maybe not. Okay, so what are we getting? Like 5, 6, appleBoxes 1, or no, appleBoxes 3, I want to check. 1E5 works. I mean, like if you were talking about actual scientific notation, then yeah, like we'd want to use like 10 to the power of 5. But for whatever reason, I'm actually not sure about this notation. It's something I started using when I was doing code golfing, but maybe it would be better to actually just write out the number, 400,000. There we go. Okay, cool. So yeah, that's good. I think that's a good number. We'll deal with that. So okay, we've reached the point here where I want to enlist your guys' help here. Okay, so basically what I'm gonna do is on my Desmos, I'm gonna pop in. Whoops, that's not what I wanted. How do I do this again? Yeah, here we go. So we're gonna have three series, okay, and we'll use some values here. Maybe we'll go with like 1. Maybe not right to 10. We'll do like 1, 2, 3, 5, 10, 20, 40, 100. How does that sound? Maybe that's too many, but we'll find out, I guess. So Y1, that's just going to be like appleBoxes 1. Okay, so we're going to start with that one, and we're going to pump in these numbers, and we're going to see what times we get. Now, what I'm going to look for from you guys is to help sum up the numbers that we're going to get. Okay, so we're going to start with appleBoxes 1 with an input of 1. Let's go. So we're going to run the tests on this. I think there are going to be about 4 or 5 of them we're going to add up. So we've got 23 plus 19 plus 16 plus 16. So let's see. I mean, 32 plus, oh, hold on a sec. Just a sec, you guys. Hey, sorry about that. Quick phone call. So it's 58. All right, thanks, Rainbow. I trust you, man. Let's keep running these. So we'll move on to 2. We'll run this. I'm wondering if it's going to time out at some point. So we get 22, 17, 14, 16. So 14 and 16 is 30. 17 and 22, so we get 47. 59? Is it 59? I think it's 59, but correct me if I'm wrong. 59. Not much of a difference on that one. Okay, these ones are looking a bit bigger, so... Oh, 69 actually? Oh, my mistake. Okay. Okay, so for this one we got 29, 27, 21, and 23. So I'm looking at the 21 and the 29. Those two would come together to form 50. So 50, 77, and then 80, 100, I guess? I think that one's 100. Whoops, not 1,000. Getting ahead of ourselves. Okay, so we'll get to 5 now. We'll run this. Okay, 30, 28, so that's 58, 27, 65, 85, I think, right? And then 25, so 110. I think that was right. We'll see though. Okay, we're getting some bigger numbers here. So we got 64, 63, so that's 127, 76, 133, 203, and 59. So 203 plus 59 would be 263 minus 1, so 262. Okay, 262. It's funny that I'm doing this manually, eh? I mean, I've got a computer in front of me. Anyway, okay. 161, 181. Oh, these are getting too tough, man. For mental math, it's too early in the morning for me. Okay, so 161, 181. What's next? 163, 156. Oh, I was trying to type it in, but I messed it up. 163, 156. Okay, so that gives us 661. This is good. These are the sort of numbers I was sort of hoping for here. We'll move on to 40. I think that was the next one, right? Yeah, 40, and then I don't even know if we'll make it to 100, to be honest. I think this one will time out. So 397. Oh, am I a wimp for not doing this in my head? Okay, let's try it. 397, 430. Well, 397 is 400 minus 3, so this would be 830 minus 3, so 827. Then 445, so let's do 27 plus 45 first. So 27 plus 5 is 32. 32 plus 40. Oh, I'm losing my numbers. What did I have? 827. Yeah, there's a lot of stuff to hold in my head, but okay, so 827. Maybe I could like write that down. I'll put it here. 827, and we want to add 45 to that. So, yeah, what was that? 32, 72, and then, okay, so it's going to be 872 plus 400. So that's going to be 1272. Whew, 1272. And then, okay, that shouldn't be too bad. 1272 plus 400 is going to be 1672. 1672, 1682, 1687. That's what I'm getting. Is that right? 1687. Great. Okay. Yeah, I'm revealing just how bad I am at arithmetic here. When I was younger, I was in university. I was taking math, and I was working at a bar at the time. And everyone there would be like, "Oh, hey, what's 15% of 4325 or something like that?" And it's like, I don't know. I'm not a calculator. Like, I could tell you about vector spaces and stuff like that, but like, yeah, like most of the servers were a lot better than me at arithmetic. Okay, that one timed out. So let's move on to the next one. So let's go appleBoxes 2. We'll start with 1. Oh, okay. Hopefully, there's going to be easier. That's a nice number. I can deal with that. Okay, great. 11 plus 11, we're at 22, 29, 37? Yeah, 37. Okay, great. We need another series. Can we get another series? I want another series. Come on. Y2? Can I do that? Yeah, Y2. Okay, so I forget the number. What was it? Oh my God. Okay, so it was 8 plus 7, that's 15. 15 plus 22, what was it, 37? Wait, 15 plus 22? Yeah, 37, right? 37? 37. 37. Okay, cool. Good. Okay, 2. Let's run that one. Okay, so we get, oh, look at this. We're getting smaller numbers. That's weird. This might be an aberration, but we'll find out. So we get 7 plus 9, so 16 plus 5, 21 plus 7, 28. Okay, so that's 28. Great. I want to rerun that first one. That's fishy, though. It was like so much bigger. So we had 11 and 11 before. 7, 8, so that's 15 plus 6, so 21 plus 8. Yeah, that's 29. I'm just going to put the 29 in, and yeah, because otherwise we've got a bit of an outlier on our hands. Let's find out. 8. 10, so we're up to 18 plus 6, 24 plus 8, 32. I can do that. All right, cool. Where are we off to next? Is it 5? Yeah, 5. Okay, cool. 5. Let's run this. So 12 plus 14, that's 26. Plus 8, that's 34. And plus 11, 45. Awesome. Oh, we're on a roll, folks. 10. 22. 26. So what's that? 48? Yeah, 48. Plus 19, so that would be 67. Plus 21, 88. I'm getting 88. Number of keys on a piano. Okay, 20. Let's run that. Okay, 23 plus 26, so that's 49, I think? Yeah, 49 plus 33, that would be 79. Well, okay, it would be 80 plus 33 minus 1, so that would be what, 113 minus 1? 112? Yeah, 112. And 100, wait, hold on. 112, 152, 155. 155. Cool. And 40 was the next one. And it might be the one, might be the last one since the other one timed out, but we'll find out. So 50, 58, well, that's 108. Very significant number. Plus 56, so that's 114, 164, 164. And then, okay, 164. So plus 50, 214, plus 5, 219. 219. Okay, that's a lot lower than the other number. Let's try 1,000. I mean 100, not 1,000. That would be too much. Okay, why did I do this? These numbers are getting big again. Okay, 81, 108. So that's 109, 189. 110. Okay, so we're at 189, 199, 299. It's not so bad. 299. 399, 394, 394. There we go. 394. Okay. And then this one, for all intents and purposes, was like infinity, I guess. But we just don't have the samples for that. We need a Y3 for our appleBoxes 3. And maybe there's a way we can like edit the colors here. I don't know. We want something kind of fun, right? I gotta say, I'm feeling kind of limited by these choices. I would have preferred a few more of these. I don't know. Red. Can we do like maybe like okay, check it out. We'll do like red fading to blue. Okay, so it's like an excerpt from the rainbow or something like that. Okay, so appleBoxes 3. We're gonna start back at 1. Let's run this. Okay, so we got 6 plus 14, so we're up to 20 plus 11, 31. And 31, 44? 31? Yeah, 44. Okay, cool. Oh, this is looking great. I love this. Okay, so now let's put 2 in here. Let's run this one. 8 plus 12, that's 20. That's 30. 42. Oh, wow, that's a really close number to the previous one. Okay, let's try this one. We'll run that. And what are we gonna get? Oh, it's taking a while. Let's look at our numbers so far. Okay, they look good. Oh, this one's taking a really long time. Okay, 6 plus 14, that's 20. 32. 45. Done. Even I can do that. Okay. Unless I did it wrong, which I probably did. Anyway, okay, let's run that again. We've got 7, we've got 15, 22, we've got 33, we've got 45. Well, hey, wow, look at that, 2 45s in a row. It's not really going up by much, is it? I mean, it's going up a little, but 7, 16, 7 plus 16 is 23, 36, yeah, 23, 36, okay, and 50. Okay, so yeah, it is going up a little bit, but is it even like, I don't know if it's going up more than a negligible amount. Wait, in the rainbow, purple comes after blue? But okay, but what I meant is it kind of repeats, right? Like, oh yeah, okay, I see what you mean. Because, all right, so here's kind of what I meant by this. Like, I meant on a color spectrum, right? So it's kind of like if we were to fade red into blue. And I'm sorry, I realized, yeah, you're probably an expert on this. You're rainbow sprinkles after all. So geez, I'm really out of line here. But anyway, I just meant like in a gradient, okay? It's a gradient. That would be a better way to say it. Okay, it's a gradient. Hopefully everyone's happy with that. Let's go back to 20 here. Did we run it? I don't know. Let's run it again just to be sure. Okay, 5, 13, so 18. 18 plus 11, 29. 29 plus 12, well, that's 30 plus 12 minus 1, so it's 41. Oh, look at that. It's going down now. Oh, okay, this is riveting. Let's run this again. So we get 5, we get 9. So what's that? 14, 8. Whoa, this one's really low, man. 14 plus 8, 22 plus 10, 32. That's like the lowest one. Okay, that feels like an anomaly to me. Let's run that again. 4, 10, so 14 plus 8, 22. Okay, 31. Maybe it's not an anomaly. We'll run it one more time just to see what kinds of numbers we're getting. Yeah, I guess they're not that much. 19. 19 plus 12 is 31. Plus 14. That's 45. I like that better. I'm cherry picking my data here, I guess, but 45. And just for fun, let's put in 100. Okay, cool. So 4, 10, 14. Plus 8, that's 22. Yeah, okay, we're back at this. What was that, 31? I just want to make sure we're getting reliable numbers, because I have a feeling like, sometimes it takes a long time to run these, and like obviously we're not getting the same numbers each time. So where were we at? That's 19 plus 12 is 31. Yeah, 31 plus 14 is 45. 31 plus 4 is 35. Yeah, 45. Okay, yeah, we'll go with the 45. It seems more reliable. Okay, so now, did it plot these? Have they been plotted? Let's see. Yeah, they've been plotted. So we're probably going to have to switch up our zoom here. Basically, what I want is something that's going to see all the way out here or so. Okay. Maybe even more. Yeah, it's going to have a perspective like that, except I want it to start at, I want it to go like not really past 100, and I want it to start at 0. So this is a bit of a trick I used to use. All you have to change is this one number now, and we'll just make it 0. Okay, so we can sort of see everything we need to now, and we're going to do some regression. Okay, so from these numbers, we can probably get an idea of what kinds of functions are going to fit this data. So, and it's not really much of a surprise, because if we think about this, this one was direct, right? It's just a single formula. It's one calculation and we're done. Well, technically a few operations, but yeah, it's just one thing, one line, one operation. Well, not one operation. You know what I mean? It's one thing and then we're done, one calculation. Whereas this, we sort of have to go through this loop and do a calculation for each iteration of that loop, but we're just doing n times n each time. So again, within the loop, it's just one operation. The difference is down here where we do this box function, because this is one where we're not just doing n times n. This is like, imagine we've forgotten the concept of multiplication, or maybe we never learned it, and we're just adding size each time. So it's like, oh, you need 10 times 10? Well, that's just going to be 10 plus 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 10. It's kind of inefficient, right? So basically, not only does this take a while, but it depends on the size. So as this loop goes on, the larger these numbers get, the longer this function is going to take. So that's why we should expect this to probably be like a big O of n squared. Well, let's find out. So this is y1. That's another really, really cool thing about Desmos. I might mess this up, but let's see. Normally, like, before I did something like, y equals 2x plus 3, or, something like that, right? Where I was just putting in the numbers. And I even did that thing where it was y equals mx plus b, where we put in the sliders and we were able to just play with these and modify them however we want. But now what I want, we don't need those anymore. What I want to do now is I want to take specifically y1, the data set that we have up here, and I want to try to fit it to a type of function. So I'm going to use the tilde here. This is for regression. Okay, so we're basically trying to look at different kinds of functions that could fit this data. Like, line of best fit, that's basically what we're looking at here. So if we wanted to try a line of best fit, we'd do mx plus b, specifically mx1 plus b. And then it's going to say, okay, well, I've got an m value for you here. I've got a b value for you here. And then it's going to give us the statistical data, the r squared value, which is like a measure of how well it fits the data. I don't think it fits all that well. It's saying that it's like very good, like 0.98 is very good, but I'm not really satisfied with it because like it's going into the negatives here, which I feel is like a bit misleading. Like even for 1, it's going into the negatives like pretty severely. It's going down to like negative 20 something for a box size of 1. That's pretty much way off. So I don't think a line is the best thing to use here. And especially, wait, hold on a sec. Didn't we have more data? Oh, right. That was the last data point for this one. We could try, if we really wanted to, we could try just like a flat line, compare it to like constant time. And we're going to see, no, that's horrible. That gives you an awful r squared value. So let's not do that. Instead, let's use a quadratic function. So we'll do ax1 squared. We're going to use standard form for now. And let me know if you want to see anything different. Plus bx1 plus c. And now look at that. That's a lot better. It's fitting the data much more nicely. And yeah, R2 for Excel. Exactly. Same thing, Rainbow. So we go through this. It's fitting the data a bit better. I like this better. I think I'm probably convinced. And, oh, yeah, look at that one. I'm probably convinced that this is a good model of the data. And we can sort of extrapolate here to say like at 100, we'd be getting, something that's like 7,000 and some. So it's no surprise that it exceeded the time limit because, I thought it was written here somewhere. Doesn't it say somewhere? Yeah, 4 seconds. Exactly, 4 seconds. So 4 seconds is 4,000 milliseconds. So basically, if we make it past, let's even put this in, y equals 4,000. If we make it past this threshold, then basically it's not going to run. We're not going to have... we're not going to be able to get numbers from it because it's going to time out. So that's why we weren't able to get the 100 one because it went past. Okay, let's see. Let's make the colors correspondent here. Yeah, nice. Okay, great. So now we want to insert another thing here. Let's talk about Y2. And by the way, let me know if anyone has any questions about this. Whoops, wrong key. What do you guys think for this type of function here? You think it's quadratic? Let's see. Ax squared plus bx1 plus c. No, probably not. Looks like if it was quadratic, it would kind of be curving the wrong way. So, and here, let's just hide that one for now, just to make this a little easier to look at. I mean, we could even, if we wanted to, we could like hide these just to sort of zoom in on this set of data. So that's probably not the best function to use. I mean, honestly, if I'm looking at the way this is growing, maybe a logistic model? I don't even know if I remember the formula for that, but it was something like 1 divided by 1, or sorry, it would be more like A divided by B minus C to the X or something like that, or yeah, something like that, right? Whoops, X1 is what I meant. Yeah, logistic model. So it actually fits, I think, better than the previous one, but I mean, come on, really? Is that the time complexity? Yeah, I think, Rainbow, you're probably right about that. It's probably linear. So mx1 plus b, it's a decent fit. I mean, it probably should be linear is the main thing. But yeah, I would say this is probably pretty good. Notice it gives us like the slope and the y-intercept that we would have here. So, okay, cool. That looks good. And then let me just like move this, I guess. And let's get another one of these in here. So we want to do y3 now. Let's get rid of this and get rid of those. So the thing about this one is it's not really doing anything. You know, like we could say it's mx1 plus b if we wanted to, but like it's going to tell us the slope is something like so close to 0, then we might as well just treat it like it's 0, right? So we could just do something like this, and it's just going to say, yeah, b is going to be 44.625. Now, I don't know if, like, it seems like it's not understanding that as being a function, so maybe I'll just do something like this, 0x1 plus b. Yeah, okay, that works better. So it's giving us the same parameter here. I'm curious why it's giving us the r squared value of 0. Isn't that like a least squares regression model sort of thing? Like, how well it fits that? Anyway, yeah, because it feels like it should be pretty good, like it's fitting the data. Anyway, okay, so those are our curves of best fit here. And the thing I sort of wanted to point out about this is it sort of matches up with our expectations in terms of our time complexities here, right? We would expect this one to be quadratic. We'd expect it to be like big O of n squared or something like that, because it has nested loops and each of them have a time complexity that depends on the size of the input. Whereas this one, we just have one loop, and yes, it does, well, okay, sorry. What I mean is this thing would depend on the size of the input in the sense that the loop would take longer if we had a bigger number in there. And then we have this one over here, which is just direct. Just give me the number, done. Okay, so basically we'd expect this one to be constant, and we'd expect this one to be linear. The thing is, normally when we have like a constant time algorithm, we'd say it's big O of 1, right? We'd say this is big O of n. And we're looking at these and we're kind of thinking, well, but this function over here, this quadratic one, for example, this is like 0.5x squared plus 20x plus 23. It's not just x squared or n squared, right? It's more complicated than that. The thing is, when we're talking about time complexity, we're talking about families of functions, okay? So when we're talking about families of functions, maybe we have like y equals a times x minus h squared plus k, a little bit of the good old vertex form over there. Wait, I want to add a slider for a as well. Is there a reason why I'm not allowed to? Maybe because I used it up there? Yeah, that might be the reason. Let's give it some other name. Let's call it P. Okay, so, and let me hide some of this junk over here. Okay, so here's what I'm trying to say. Like, all of these are parabolas, you know, all of these are quadratic functions, and yeah, that's barely moving it, but like, no matter how we move this thing around, they're within the same family. When we're talking about time complexity, we don't really make a distinction between something like this and something like this, because what we care about is how it grows. We care more about like the derivative of these things than we care about the functions themselves. So whether it's something that looks like this or something that looks like this doesn't really matter. You know, you can see that this is growing slower than this one is growing, but in terms of the time complexity, it's considered the same because they're both quadratic, as opposed to like, you know, if we had like an exponential, which is just like, you know, right into space, like, geez, you know, it doesn't take long for that one to just totally surpass the threshold there. So these are not the same thing, you know, like you could even take something like this, like, okay, this is a really, really weak exponential function, you know, like even more so. We can give it this like really, really slow rate of growth, but it's still, like, you could make this the smallest number you can think of, and still, unless it's 0, and still there would be a point where the exponential is gonna surpass the quadratic. And even if you made the quadratic like so steep, you know, you make this number huge, you make this number tiny, still, you will always reach a point where the exponential is going to surpass it because it grows faster. So that's why when we're talking about time complexity, we're not talking about the specifics like what number do you have here? What's your A, B, and C? We're talking about what family of functions does it belong to? Is it something that's quadratic? Is it something that's linear? Is it exponential? Is it constant? What family does it belong to? Now, there's another pretty huge point I want to make about these things, and I need to sort of zoom in to make this point. Take a look at this, and in particular, let's even hide these guys here, and even this. So this is another really massive point I want to make about time complexity. Check it out. So we would normally say, like, this is a constant time algorithm, right? This is a big O of 1 algorithm, and let's even comment those in. So this would be big O of 1. This one would be big O of n, and then this one down here was big O of n squared. Okay, cool. So we have 3 different complexities, but keep in mind, even though the time complexity is better on this one, that doesn't mean it's always going to execute faster than these other guys. So if we take a look at this, check it out. It actually takes a longer time at first. For the first few of them, right, for the first 2 at least, it took us a longer time to execute this one, the blue one, like the constant time algorithm, than it did to execute the linear one. So, you know, like we can see these points down here, they're lower than all of these ones over here. That's kind of meaningful. But the main thing is that in the long run, eventually, that's not going to be the case. We care about how it grows. We don't care as much about the exact execution time, so much as how that execution time scales up according to the size of our inputs. Now, having said that, if you're talking about like a production app or something like that, then yeah, we care about all of it. We're going to care about the execution time. There are going to be micro optimizations that we can make that are going to reduce the computation time. There's actually one that a guy pointed out to me a while back that I think would fall under this category of like a micro optimization. It's this right here. So if we put in math.pow instead of using the ES6 exponentiation thing, it tends to be faster. And I guess maybe I'm not proving that point very well because these are all bigger numbers. Anyway, point is that would be an example of like a style of micro optimization. We're not changing like the structure of the algorithm. We're not changing the design of the algorithm. We're changing some of the specific functions that we're calling within it because they happen to run a bit faster. Okay, so that's basically the idea with that one. Going back to Desmos over here, there was, I think, one more point I wanted to make about this. I think, was there? Let's see. I don't know. Anyone have any questions about this? I might have said everything I wanted to. But, oh, no, I didn't. Okay, so yeah, I wanted to talk about big O specifically because when we talk about time complexity, we tend to use big O, but technically there are other ones, and I don't totally know the difference between them, but I think it's something like there's also big theta and big like omega, I think, and I think they correspond to like worst case, average case, and best case. I'm probably butchering that, but I think it's something sort of like that. Let's search it. So time complexity, big O theta omega. Let's try that. Stack Overflow, that's probably trustworthy source. Okay, so they're talking about it here. If an algorithm is of big theta of g of n, it means that the running time of the algorithm as n input size gets larger is proportional to g at n. Oh, at most proportional. Yeah, okay. So basically big O is kind of like a worst case, and big theta is kind of, I guess, average case, right? Oh, okay, upper bound, tight bound, lower bound. Yeah, that's basically it, right? So this is like worst case, worst case, best case, and average case, I guess, right? But not exactly, because I think you can only have a tight bound if the upper bound and lower bound kind of meet with each other. I don't know, I'd have to read more about this. It looks like this user has, community wiki. Okay, no wonder it's such a good answer. Anyway, I'd have to read through this a little more, but that's basically the stuff I wanted to say about time complexity for today. You guys let me know if you have any questions, comments, or concerns, but I think we're probably good for appleBoxes here. Yeah, we passed it, right? So I don't think we need to go any further. Yeah, so I think that's going to be it for today. Hey, thanks everyone for tuning in.